do that again. Yeah, so this is Tales from the Typos Frontier. In particular, it's a story about the Code-Brown representation of syntax that we use, and it's the sort of gnarly invariant that it really helps if you have a nice type system to not screw up. But because we're idiots, we do it in Haskell. Real well. Yeah. Of course, our secret weapon is that every time our Haskell program falls over in a heap, we go back to our Agda version of it, fix it up, and then port back to Haskell what we did in Agda. So the fancy type system it might not be in the production version, but it's certainly how we figure out what the hell we're playing at. So let me tell a story about some data structures with some gnarly invariants, because what else is there to life, or at least to mine. Okay, so the things that we do, we are always indexing stuff by specific notions of scope. I'll tell you what a scope is in a moment, but most importantly at the moment, there are Fortran conventions, things near the beginning of the Greek alphabet will be scopes. So gamma and delta will be scopes, and then there will be things that live in scopes. So in particular, we might have a term T that lives in scope gamma, and you might think, hang on a minute, if he's trying to do something with vibrations, that's dead upside down. But it's not a vibration, it's an indexing, so it's the right way around. Gamma comes first, and then T has to behave well. But when I write T below gamma directly like this, I mean not only that everything in T is scoped by gamma, but also that everything in gamma occurs in T. So this is saying T is relevant for gamma. Right, so in the sense, everybody's got to be somewhere. All the variables in gamma have to occur at least once in T. We'll show how to explicitly slacken that condition shortly. Likewise, there will be substitutions, simultaneous substitutions that map gamma variables to delta terms. And these substitutions will also be relevant. That is to say, every variable in delta occurs in the image of at least one gamma variable. So the talk in a nutshell is how to get around to making sure that the action of the substitution preserves relevance. So that's to say that if you act on a relevant term with a relevant substitution, then every term in the target scope, every variable in the target scope will occur in the substitution image. So let's see, I don't know how many, what the interaction structures we're going to need for the diagrams in this, but we can see we need at least two. So if you don't know what I'm doing, I'm going to tell you. So the idea is that diagrams are colored so that you can see the quantification in the theorems they represent. So, so in particular, black stuff is played first by the universal quantifier, blue stuff is played second by the existential quantifier. So that is to say, given gamma, delta, sigma, and T, T sigma exists with this property. I see a hand.
Am I audible?
Yes.
Do you take requests?
Depends what they are.
So one point about surjections is that they're compositional, but they're not decompositional. So I can have two things that are not surjective, put together, they are surjective. Could you highlight how you deal with that as you go along?
I can, well, I'm certainly willing to accept further interruptions.
Okay, thanks. Sorry about that. I'll shut up now.
Okay, so so I hope we at least got as far as what this is intended to symbolize. But now we need to figure out, that's the high level thing. What actually are we mucking about with? So we need to get around to talking about what code-around things are. So, so this is relevant subs acts on relevant term relevantly. Okay, so what is a code-around thing? So if we want to say some variables are in scope and we don't have to use all of them, then what we do is we first throw out the ones we're not going to use. Is that the same hand as last time, Ohad? Or is this a new hand?
It was an old hand, sorry.
Yeah, so we first of all throw out the variables from the scope that we're not going to use, and then we make sure we're relevant in the ones we keep. So that's to say, a code-around thing, and the things will usually but not always be terms. A code-around thing is the pair of a thing and a thinning, and the code-around thing lives in scope gamma. So this thing means that T is relevant for some subscope gamma hat, which injects into gamma by some thinning theta. So I'm going to write upward non-arrows to indicate thinnings between scopes, and I'll usually give them Greek letters that are like theta or phi, or something that makes that kind of hissy noise. Yes, so something which is either theta short for thinning, and phi, which is short for thinning, which is the same word in Cockney. Okay, so what are these thinnings? We're representing, on the one hand, if you think up the way, we're representing monotone injections. If you think down the way, we're talking about selections. And in general, these things work for lists. So you might have variables, you might have a multi-sorted language in which the variables can take different sorts, and we would be distinguishing those sorts. Or if you have only one sort, then lists of one are natural numbers, are they not? And what you end up with is exactly binomial coefficients. So effectively, what we're talking about is, in the case of binomial coefficients, is bit vectors that are selecting stuff, where we index by the length, but also by the population count. So we're talking about bit vectors of a given length with a given number of ones, corresponding to the things that we selected. But you can do it with lists, and indeed, I will do it with lists. So for example, we might have a list of letters, T-A-I-N, and if we select from that by 1011, we get TIN, and then if we select from that by 001, we're left with just N. See what's going on? And then these compose. The way you do it is that you read the ones in the top edge, the top arrow, top thinning, as the places to put the things in the bottom thinning. So you do a substitution. So I'm going to substitute 0, 0, 1 there and end up with 0, 0, 0, 1 as the composite thinning. So these are a category with this composition, with the identity being all ones, the full, all the bits set to 1. And of course, they're also monoidal category. So for example, I can fill in like maybe this composition is just made from like the identity on 2 things, and maybe what shall I pick? Perhaps the chemical symbol for plutonium. And these just plug together side to side. So that's what they are, and they behave like injections upwards, selections downwards, and they're the monoidal category on singleton costate, if you want to put it that way. But so yeah, anything you can build with wires and one of those without crossing the wires. So they represent selections. Okay, so what does that give us when we start? Sorry, yeah.
The arrow from Putin to Team. It seems like it doesn't have the right number.
Sorry, no, it's you have to concatenate.
Oh,
okay. Here I concatenate by immediate juxtaposition, but yeah, the monoidal operation is exactly concatenation of the bit vectors and of the words. So yes, this is that's why the French are very careful to pronounce poutine, because obviously greasy fries. Anyhow, where did I get to? Yes. So what have we got? Let's explore how to build some terms, some relevant terms with this technology. So what happens? So I'm going to write. I'm going to have only one sort today in my terms. I'm going to write the singleton thing. So these things really will be numbers. So maybe I'll actually write numbers. So variables look like some sort of indistinct leaf-like object that hangs from the number 1. So that's to say, on the discipline that you have kicked out of scope all the things you're not going to use at the earliest possible opportunity, then by the time you are deciding to use a variable, there had better be exactly one variable in scope. So there's no doubt about what it is. And then by the same token, let's talk about how variables come into scope. They come into scope with a lambda. So when you deploy a lambda, a new variable comes into scope. That's to say, if you want to say why lambda t is relevant for gamma, then you better explain why t is relevant for gamma plus 1. That's to say, if you bring it into scope with a lambda, you have to use it. If you weren't planning on using it, if you want to write a syntactically constant function, you better not bring it into scope in the first place. So we also allow constants, kappa t in gamma, if and only if t over gamma. So that's 2 ways to make abstractions, relevant abstractions and constants. And if you really want to implement a relevant logic, then you just ban constants. But it's at binding at the very binding site, you promise whether or not you're going to use it. Okay, so let's have an example that we can do so far. Good old-fashioned combinator K from combinatory logic, which you would normally write, you've got some constant, you've got some environment, you ignore the environment and give back the constant. Here, that is lambda kappa box is a closed term. We're saying, you know, we keep the first thing, we throw the second thing away, and we give back the thing that we didn't throw away.
An empty context on top.
Yes, it's a closed term. Okay, so, but you know, life's pretty boring if we have only binding operators and variables, because all the functions that we can write are going to be picking one. So how the hell do we deal with stuff like application? Okay, let's get myself some fresh board. Okay, so what do pairs of things look like in this setting? Well, so we've got some scope gamma that we want our pair to live in, and it might well be the case that not everything in scope gamma is used on both components of the pair. So we're going to select a subscope gamma naught by some thinning theta naught, and a subscope gamma 1 by some theta 1. And we're going to make sure our left component S is relevant for gamma naught, our right component T is relevant for gamma 1, but that's not enough. We have to ensure that everything in gamma is used either in S or in T. So we have to ensure that these two thinnings form a covering. I'm going to write that, and I'll even write, there's a kind of notion of what is the evidence that the thinnings form a covering, and they're bit vectors, right? So they form a covering if their bitwise disjunction is all true. Yes. So let's see the question. Okay, yeah, so the question is, I don't know much about the context of this work. Is this describing a type theory where the category of contexts is relevance monoidal? So I want to be clear that I'm not particularly in the business of enforcing that the type theory is relevant. I'm choosing a particular representation of arbitrary terms that exploits relevance to achieve a canonical representative of each alpha equivalence class. So I'm basically saying where de Bruijn uses numbers to represent variables, and at the variable use site, you pick a number and implicitly you throw away the other numbers. Here, the throwing away has to happen as soon as possible rather than as late as possible. So that's all that's happening. It's a crafty representation of general terms, which exploits relevance as an invariant in the construction rather than as a property of the logic that we're working with. Of course, as I said, if you want to enforce relevance as a property, I mean, you can play all sorts of these games. If you want to enforce relevance, then you forbid constants. If you want to enforce linearity, then you insist not that the thinning's disjunction is total, but that their exclusive OR is total, that each variable goes left or right, but not both. So one could refine this system to enforce particular properties of the logic, but not today. So these are, so I hope that's useful. Yeah, and then we can also have atoms, like if you had a unit type, you might want to represent the empty tuple or void. So that's just some atom that lives over an empty, that lives under an empty scope. Okay, so we've got atoms, pairs, binding variables. We're in reasonably decent shape. And then if you're us in typos land, you also have second order variables which are not managed with the same discipline. So we know we have meta variables M, which are also scoped. So that's to say, a meta variable with scope gamma can be instantiated with any term that uses some or all of the variable, none, some or all of the variables in gamma. The idea is we know what the meta variable's scope tells you the permitted dependencies of terms that may be used to instantiate the meta variable. And then if you plug a meta variable into a term along with a substitution, and this whole thing lives in delta if and only if the substitution is gets you from gamma to delta. It has to be a relevant substitution, otherwise this wouldn't be a relevant term. Right. Yep. Ohad?
Hello, can you hear me?
Yes.
Are you going to give a more concrete representation, or is this the representation you're going to use?
Well, I could. I'm deliberately doing this talk on a board rather than with an Emacs window, so that we don't get bogged down. That's
fine.
Active. So, but all of these things, so I mean, I represent the scopes by backward lists because they grow on the right like context. Effectively represent the thinnings as an inductively defined analog of bit vectors. These things, evidence that we achieve covering is also inductively defined.
Yeah, how?
Indeed, the really sensible thing to do in this setting, I digress, is to use the relational presentation of composition.
Okay, yep. Thanks.
Yeah. So in particular, if you want to say what a pullback square is in this setting, it really helps to have an inductive definition of what it is to be a composition triangle.
So where shall I look? Shall I look at Programmer Comacon if I want to see the concrete thing?
There is definitely something of that in there. I can point you to, well, okay, the current version's a nightmare because my marking got in the way.
Okay, I'll watch this space. That's okay. I can do that. Thanks.
But yeah, there's a bunch of that stuff. There's also a bunch of that stuff in the typos repo in the kind of AGDA sections because like I say, we screw this up every time we try and do it in Haskell. Right? In Haskell, these bit vectors that represent thinnings, they are just integers because they're wide enough, and we just do deliberate bit twiddling, and it's really easy to mess up. Okay, so I got as far as okay, yeah. So what's actually going on here? I should give the game away. What we're really insisting on here is that this is the lurking fragment of a coproduct diagram. If you imagine there being some even larger So, you know, if you think that gamma is the support of the pair, but maybe back in the day, there were even more variables in scope for the whole term that this pair is only a part of, then you'll have some gamma prime. And so here, gamma naught and gamma 1 will be subsets of gamma prime, and gamma will be their co-product in the slice. So this, the category of scopes and thinnings does not have co-products, but a slice category does. And that's exactly what we need for computing these covers. We compute the smallest subset that both of these two embedded, and we end up. I mean, what's going on here? I mean, we're just doing Boolean logic, right? We're fiddling around with bit vectors, doing pointwise Bohr on them. It's not surprising that we kind of end up being able to reason about these things by the universal product property of co-products. Yeah.
So if you think of the things as like injective functions,
Yeah.
then what are the co-products?
Well, so that's the point.
Okay.
They don't have co-products, but the slice category of those things does.
All right, because the co-product of injective functions is injective.
Yeah. Yeah. So you think of the slices as starting with some fixed universe, and then saying an object in the slice is picking a subset together with the thinning that embeds it into the universe.
Okay.
And then those subsets have intersections and unions with similar embeddings into the universe, so that you get yeah. So so it's co-products in the slice, and similarly, well, so exactly pullbacks behave sensibly and give you the notion of intersection, which becomes really important when you talk about pattern matching. But that's definitely another story. What I wanted to do, having written down the K combinator, I just wanted to write concretely the S combinator as an example of a thing that does a thing. So S, if you remember, takes a function and its argument and an environment and distributes the environment to both pieces, which is why it gives you an implementation of functional programming. And what is that in this setting? It is lambda, 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 because we can see all of these variables get used somewhere. And then we have a pair, which is 101, 0, 1, 1. And then we have another pair, which is 1, 0, 0, 1. So Bob likes to joke that de Bruijn indices are a good Ceylon detector. They're not for humans. And yeah, this is this is definitely not for humans, but it's still lots of fun. At least I wrote the numbers in binary, right? To just spare you that misery. But you can, you're directly watching the wiring happen at each junction. So that's the key concepts involved. We've got our constants, we've got lambdas, we've got pairs, and we've got these. I haven't done the meta variables. That happens some other time. Okay. So so what happens next? So how do we, in particular, how do we push a relevant substitution into one of these pairs? Right. So we know that only some of the stuff is used in the left component, only some of the stuff is used in the right component. So we need to be careful about what we do to our substitution. So there's a handy operation. So that's the general sort of situation is that I have some relevant substitution that gets me from gamma to delta. But then, because I'm going into one or other component of a pair, I don't want all of the gamma. I just want some gamma naught. So what on earth am I going to do? Well, I'm going to throw some stuff out of my substitution. I'm going to keep only the entries. My substitution is a vector of terms. I'm going to select from that vector only the things in the position that are selected by theta. But that means I potentially use fewer of the target variables than are in delta. What's going to happen? I'm going to compute a substitution theta sigma, and I'm going to compute a scope delta naught, and that will embed into some into delta by some theta prime. So that's the point, is that given my thinning and my relevant substitution, I can complete this this square that gives me the restricted version of the substitution, and it's how its support embeds into the overall support. And then, so correspondingly, I take the thinnings that get me, or seen as dually as selections, that take me to the left and to the right, and I use them to chuck away parts of the substitution. So this is now something that can act on a gamma naught relevant term and give me something which is delta naught relevant as a result. So how do I obtain the overall objective? Well, I have to so I have to explain how to do a relevant substitution to each of the constructs. Well, I haven't told you how to build a relevant substitution, but I'll tell you now. A relevant substitution is built by a gamma-fold iteration of relevant pairing. So I'm really just representing a substitution as a tuple, which is the right length, constructed by relevant pairing. So let's do some easy cases. When we reach a variable, it's the only variable. So our vector of terms that would give us the images consists exactly of the term that's going to replace the vector. And correspondingly, straightforwardly, if the substitution is relevant for the target scope and it consists of a single term, then that term is relevant for the target scope, so we're happy, right? Okay, so that's variable use sites. Likewise, if a substitution acts on an atom, then fantastic, we know that the substitution is empty, and we just give back the atom we first thought of. We note that if the source scope of a relevant substitution is empty, then the target scope is also empty. Simply because every variable in the target scope has to be in the image of a term in the source scope. And if there aren't any variables in the source scope, then there's nowhere for variables in the target scope to hang out. There are no images for them to occur in. So the target scope must be empty. So that's fine. How about going under binders? Well, if your binding operator is the constant kappa, then your substitution is good, because it's the same scope both places, and you can put the kappa back. If your substitution is, if your binding operator is the lambda, then as usual, you need to figure out how to push the substitution under binder. So what do? You build the relevant pair. That. So yeah, let me just buy back some real estate. So what we're saying is, what is the action of sigma on lambda t? It's equal to lambda of t acted on by the substitution given by sigma here and the variable here. This is a bunch of zeros followed by a 1, and this is a bunch of 1s followed by a 0. And nobody shifted anything, right? We didn't have to walk through the substitution sigma, tweaking all the de Bruijn indices. At the outermost point, oh yeah, and we can see, of course, that these cover. So at the outermost layer, we said our old substitution doesn't use the new bound variable, and our new substitution, our new entry, our new image is exactly the new bound variable. Inductively, we're guaranteed that this will have a relevant result, and correspondingly that the bound variable will occur in the image, so that it's appropriate to abstract it with the lambda. So that's the nice thing. And the tricky part, which is why I've left it, is of course to push the substitution through pairs. So what happens? I'll draw this at a slightly, I want to draw a three-dimensional diagram, but it's a bit tricky. I've got some gamma, I've got a substitution that gets me to delta, and then I've got a pair that selects by theta naught and theta 1, gamma naught and gamma 1. Got some S, some T, and these form a cover. So we've already established that I've got my two selections, theta naught and theta 1. So I can now do the construction I mentioned earlier. I need to take sigma and refine it to each of gamma naught and gamma 1 by pushing down the selections. So I build these squares. So it's theta 1 prime, delta 1, and this is theta 1 sigma. And similarly here, this is theta naught prime, theta naught sigma, and delta naught. And the crucial thing, the tricky part, is to show, I mean, I can certainly use this substitution on S and get a term that's relevant for delta naught. And I can use this substitution on T and get a term. So yeah, let's do that actually. This is S acted on by theta naught sigma. This is T acted on by theta 1 sigma. And the problem, which I will use a red pen for, is to show this. To show that the thinnings that we get that embed target scopes are also a covering, right? We want to put these two things, we want to put the image of S and the image of T together to build a relevant pair with support delta. That means we need to know that these two thinnings cover the whole of the target scope. And at the moment, that proof is a pretty grungy piece of Boolean logic. I mean, essentially, the argument is this. is a kind of negative one. It's like, suppose these two thinnings didn't cover delta, then there would be a non-trivial embedding from their co-product into delta. We would be able to find something in delta that was missing. We would be able to find at least one variable in gamma which had the missing thing in its image. And then we would need to say, but hang on a minute, because the source term was relevant in gamma. That can't arise. But at the moment, I do a proof by induction over the covering explanation, and that tells me what miserable theorem about disjunctions I need to import from Boolean logic to the category of things. So yes, I've got a plan to at least make the nasty Boolean logic something a machine does rather than me, which is one reason why I've been poking about in my dad's thesis looking for simple algorithms for doing tautology checking. Right? Every Boolean tautology gives you a true fact about the transformability of diagrams in thinning land with co-products and pullbacks. Those are the disjunctions and conjunctions. So you want to be able to say, you know, if we have this diagram, then we always have that diagram. And very often that corresponds to just doing bitwise, point-wise Boolean operations on selections from some universal scope. So they turn out to be really boring as things to bash out by hand, theorem prover. But I'm basically hoping to do some kind of weaponized sequent calculus prover that just kills them for me.
Can you hear me?
Yeah.
So this coverage proof, do you care about its intentionality? I mean, of course, you want it to be computable, but do you care about how you prove it, or you just want it proved in an elegant way?
Yeah, I'd rather. I mean, so okay. Crucially, coverage proofs have no bits in them. I mean, actually, one of the delightful things about working in this setting, and it's deeply ironic. The rule of thumb when
they could have bits in them. It's just that you choose not to have any bits in them.
Yeah, I choose not to have any bits in them. All the bits.
Okay.
Right. The fact that so given the two thinnings, the fact that they form a covering is just a thing that you check, right? There's no two ways they can form a covering.
Okay, I'll send you a message later then. Thanks.
But yeah, the joyful thing about this is that when you work with all of these inductively defined two-dimensional or higher dimensional things that contain no bits whatsoever, when you program, you work explicitly with the highest dimensional objects available, and you leave all of their indices to be inferred by unification. So it really is the situation that you program by explicit pattern matching and construction of data structures that contain no data. And the actual program is filled in by the unification algorithm and is nowhere to be seen. I mean, it's being brought into existence by the thing calculating what the only indices have to be. But we are literally calculating a program from its specification when we do that. We are being explicit with propositional stuff that are going to get erased at runtime in order to force the computer to infer what the algorithm has to be. It's delightful. It's the exact. This is not programming in standard ML. The actual thing that gets executed is, as far as possible, completely invisible, and the program that we write gets erased. That's what progress is. So yes, I'm not quite there yet, but nearly. How am I doing for time? It sounds like a good time to wind up, so well. But yeah, it seems I've got a bit to go. I've certainly done the proof of this, and I can do the construction that actually gives me the substitution action and shows that it's relevant, and that's nice. The next thing I want to do is, well, okay, what I haven't yet got is that substitution compose nicely. And it's simply just the pair case is yet more gnarly theorem proving that I want a theorem prover to do rather than me. So I'm kind of hanging back on that until I've got a better stick to beat that with. And then hopefully we'll establish that these sort of substitution refinement squares, I mean, these things that we had, which was sort of gamma, gamma naught, beta naught, delta, sigma, inducing delta naught, beta naught, sigma, those things. These things paste together. I mean, they certainly have the property that if you select all of the things from gamma, so you pick this to be the identity, then gamma naught is the same as gamma, and you get the whole of the substitution. You don't throw anything out of the substitution. So this also is the identity. And you get that these compose. If you throw some stuff out and you throw some more stuff out, then you might as well have just thrown it all out in the first place. And they also ought to paste together side by side. Yeah.
I'm wondering if the squares are fullbacks.
Well, they're not. Well, they're not in the same. So these are thinnings and these are substitutions.
I guess you can maybe. I think of them maybe as all as functions.
Yes.
That's in functions, and then because it's surjective, the substitution.
Yeah, so it's quite likely actually in that sense.
Okay.
So certainly thinnings seen as acting upwards are a special case of substitution. Relevant substitutions are also a special case of substitution. So it's extremely likely that if you embed these pictures into the category of non-relevant substitutions, which they certainly both do, then you'll get pullback.
Both says they are least local independence components.
Yes, I'm left none the wiser. But yes, I'm expecting that these behave nicely like some flavor of double category, since they paste in both dimensions. So yes, I want to get back to this. It's also really, this is lots of fun as a kind of category theory you can get away with doing in AGDA without even switching cubicle on, because everything in sight is not merely small, but first order, right? You know, our morphisms here are bit vectors or term vectors, right? You know, they have uncontroversial on the nose equality. We don't have to work up to extensionality or up to any quotients. So we can be, you know, ridiculously naive about what we say a category is, and have a lovely time. Yes, so that's a fun thing to do. It's even nice to explore So this is a sort of new digression that's causing me to like mangle my entire construction, delete everything, is that it's nice to think about categories which have finitely many objects and finitely many arrows, which are not identity arrows. They're so finite that you can just check that you can ask for a definition of composition. You just ask for how the non-identity arrows compose with each other. And then because everything's finite, you can just bloody well check it's associative by brute force. And then the point is that functors from those categories into some other place are diagrammed. And so we might even start thinking, yeah, what's bothering me is that I'm constructing limits and co-limits on an individual basis, rather than just saying, this is what the diagram's like, this is the best one. You know, so I want to achieve that level of abstraction, and finiteness is a really great place to do that. And what would be cool then is if someone then actually let us draw the bloody diagrams. Because I'll tell you one thing that happens when I'm doing this stuff in Agda is that when I'm looking at my kind of Agda information buffer with loads of variables that stand for various kind of composition triangles and covering evidence and all of that sort of stuff, I cannot see what the hell is going on. I have to carry my Mac over to my whiteboard and construct the diagram that is being described in this context. Figure out what the construction is on the whiteboard and then translate it back to Agda. So it really is a situation where there's something very visual going on that Agda totally isn't showing us. So it would be lovely to fix that up. Anyhow, I think it looks like time I should shut up.